All right, hello everyone. It's Mr. Johnson. Um, so before we get started, I just want to preface this recording with I am at home in my office. So if you hear my phone buzzing or clicks or my cat meowing or something like that, you know, um, it's going to happen. It's part of real life. All right, so today we're going to talk about manufacturing processes, um, specifically the primary and secondary processing of materials. Our target for the day. I can identify the process by which products are created from raw materials by reviewing primary and secondary manufacturing processes. We're also going to talk a little bit about how you select those processes as well. Alright, so today we're going to review the primary manufacturing processes, what they are, and the common forms that they take. So we've got some images over here that kind of go along with that. And we're going to review the secondary manufacturing processes and the forms that they take as well. That's where the bulk of our time will be spent. And then we're going to take a little bit of time at the end and talk about why one process would be chosen over another. This is actually really important, but sometimes it's just very self-evident, so we'll talk about that in a bit. So, why is this important to know? Our lab, our shop, every other lab or shop or manufacturing facility in the world definitely doesn't have every process available. It's just a matter of practicality, space. It's really difficult to have some of these processes in the same facility area, and there's very few companies that specialize in everything. At least being aware that there are other options out there is really important to kind of know. It's also important to sort of understand that companies rely on subcontractors and things like that to get things done that maybe they don't specialize in or have the equipment for, because it's just not cost effective for them. So we'll talk about cost as well with a lot of these processes today as well. And then we'll understand the reasoning for process selection. Again, a lot of that does have to do with cost, but there's other things involved as well. And then we will also want to know the reasoning for the selection. So what have we learned up to this point in the school year? So again, I know I'm also making this recording for some other classes and other teachers, but for our class up to this point in the year, just so everybody else can frame that, all the processes we've learned have primarily been secondary manufacturing processes. So we learned with our sheet metal projects, shearing, cutting, we did some forming there, we did some joining, and then we do some drilling and some grinding. We've done joining in terms of welding, we've done soldering, we've done brazing, we've done bolted connections. We'll talk about all those later on. We've bent metal, we've done all sorts of things with forming, and then we've cut metal in various ways as well. And then the one primary process that we kind of have done, but we've sort of focused on that as almost a secondary process, trying to produce a finished good, is casting. So we'll talk about that as well. Alright, so primary manufacturing. What is primary manufacturing? So this is when you take raw materials and you turn them into some sort of standardized stock. So usually it's not how you're going to get a product. There's very few primary processed materials that the average consumer buys. A good example of something like that, though, would be stuff like 2x4s and things a lot of that nature from Home Depot or Lowe's or whatever. But your average consumer isn't buying, 20-foot bars of rebar from the plant that made them, and even then, those have had some secondary processing done. But some examples of primary manufacturing are casting. Okay, metals and plastics are cast. Basically you melt down the ingredients, you mix them together, and then you produce some sort of casting. With plastics, they're synthesized usually from a petroleum product, and things are mixed and processed and catalyzed until you have a polymer, and then you extrude them. and then you turn them into various types of standardized stock, usually plastic pellets. We'll talk about that in a bit. Um, and with metals, this image here actually kind of shows what you would do with what's called a continuous casting machine. And again, this can apply to both metals and plastics, but basically you take your pouring ladle, which has been filled with a molten material, then it goes into the pouring basin. It goes down through this specialized tool here called the mold, that actually is basically lined with water, and it attempts to cool and solidify the material as rapidly as it can, so that it can then be solidified by the time it gets to just to the mouth of the part here, and then it gets down here and it's formed by rollers into some sort of standardized slab, and then in the case of steel at least, cutting torches cut it off. If this were aluminum, you'd probably shear it off. If it were plastic, you'd definitely have a shearing process cutting it up if you wanted pellets or bars or something like that. So this is one example of a primary manufacturing process. Another primary manufacturing process is extrusion. This is probably one of the more expensive ones. It's also really good for high production rates. So a lot of companies get custom-made extrusions for things that they want to manufacture. So things like metal window frames are often extrusions that are then cut and bent and joined. Plastics, all sorts of custom extrusions there. And then ceramics, if you think about bricks, one of the ways that bricks can be manufactured is that they're actually you take a bunch of clay in an area like here, and you run it through this main ram, and then you extrude a rectangular shape, and then you get this long rectangular prism that can basically keep going almost indefinitely, and then you cut the bricks to width or to length, and then they're set off to dry. So that's how you would do that with ceramics. With metals, so this is a piece of aluminum here. You can, especially with aluminum in particular, you can get a lot of crazy shapes that just lend themselves to ease of manufacturing, and it saves material in the long run. Extrusions are almost wasteless in the raw form that they come in. You're not cutting material out, you're forming the material to that shape. So a lot of advantages with extrusion there. And then plastics are primarily done through pelletizing from the manufacturer. So you can see there's all sorts of little clear pellets here, and then colorant and sometimes other types of plastics are added in before they're melted into, say, an injection molder or something like that. So this is how a lot of companies receive their raw plastic stock from a primary manufacturer. And wood, there's very few other primary processes other than milling. So these two images here, this is just kind of a nice digital image of how a log might be cut up into boards. So you can see the whole log and various cuts here. And then it's done with a sawmill. So you can see this is basically a big bandsaw, and the blade would go around like this. And it cuts through the log, so this would be the cut that's being done here is similar to this cut. It goes down the entire length of the log, and then slabs are cut off, and sometimes the slabs are then rotated and recut and resawn. So these are just examples over here of various sizes of boards that are taken out of logs, but that's how a log gets turned into a usable piece of lumber. Ceramics. Ceramics are interesting in that it takes a lot of refining to take an ore and turn it into a usable ceramic powder, and even then a lot of them get blended either at the secondary manufacturer who buys raw ingredients and blends them, or some primary manufacturers will pre-blend things just because that's what they're looking for. But in the end, they have to get ground down to very, very, very fine powders. Sometimes binders are added, so sometimes they're turned into a clay at the primary processor, but usually they start as a powder. Alright, so that's the gist of primary manufacturing, so let's look at secondary manufacturing as well. So basically, what secondary manufacturing is we're taking the raw material that's been standardized to a stock. So a factory, a shop, anybody that makes stuff. Our shop, our lab. In our case, I order bar stock. So we get steel that's been mixed and molded into bars. Eventually, it gets rolled into the bars, and then I order those bars, and they're just standardized steel bars that we order, which is why they're cost effective. They're pretty inexpensive. Um, and then we would be considered like a secondary manufacturing facility where we take those bars and we add value to them. So we're taking that standardized stock and we're adding some value to them by doing these various secondary manufacturing processes we're going to talk about in a little bit. So in a lot of cases, finished parts are sold to other industries, so additional secondary, tertiary manufacturers, or directly to consumers. So in some manufacturing facilities, they do both. They'll take standardized stock and they'll produce items that they sell directly to their consumers, or parts for other manufacturers to then incorporate into their manufactured assemblies as well. And because of there are so many choices with similar operations, you really it depends on the material, it depends on all sorts of different things, and again, we'll talk about how you choose them. But there are similar ways to get the same result in secondary manufacturing. It just depends on a few different factors like cost and the material and the precision that you want. So we'll talk about that in a second here. So some secondary manufacturing processes can be broken down into these 7 categories, and you'll find different breakdowns of this, and we're going to break each of these down even further. But these 7 seem to be the most common that I've found over the years in some basic research and things like that. So if you were to Google secondary manufacturing processes, you get lists approximately like this. Some people put casting and molding into the same category, and some people put like additive, that might go up in here too. Conditioning gets left off a lot, but I do think that's important, especially because we do focus on metal and steel processing in particular in our lab. So I think talking about conditioning is important. All right, casting. So we'll start with secondary casting. So we already talked about casting, what it is. You're taking a molten material and you're forming it into some shape. In this case, we're talking about taking whether it's ingots that have been produced and very refined alloys or plastics or what have you, and we want to produce semi-finished goods from them. We have to make a lot of specialty tools and things like that. So we start with a refined material, and then we're gonna look at 3 processes here. So let's go back here. So die casting. We have usually a steel die. They can be aluminum. They can be tin, depending upon the material that we're casting. But let's talk about, say we're going to die cast aluminum, or some people call it like white metal. It's really soft, just a mixture of different metals, usually a little bit of aluminum, some tin, random stuff. It's what old car emblems were made out of and things like that. Really kind of cheap parts. A lot of toys used to be made out of this too. So if you get die cast toys, they're usually not like heavy duty aluminum or steel. They're like a mixture of cheap metals. So usually with die casting metal, you start with a steel die. It's water cooled, so running through this mold here would be jets of water and things like that. And then we inject the molten metal, so aluminum or tin or something like that. And they're injected at a very high pressure, and then they cool inside the die, and that water really rapidly cools them down. And then you get a very highly refined, highly accurate product, because basically there's nowhere for for the metal to shrink or expand or anything like that. So, assuming your die is made very well, it's very accurate. However, look at how intricate these molds can be, and this is honestly a rather simple one. They're very expensive to make, especially if you think about hardened, polished steel, things like that. So you'd want like a high production rate with die casting. You want to make a lot of stuff in order to make your money back. Investment casting, however, that's actually really easy to do one-off pieces and things like that. So here we take a wax positive image. What that is you essentially carve what you want out of wax, special wax usually, and then you dip it in a ceramic liquid. Usually that ceramic is plaster, and then you can add backing materials and things like that. But basically, you repeatedly dip and dry the ceramic liquid till it forms a coating outside of the wax. So once the ceramic cures, it's now heat resistant. So it can be very lightly fired, and then the wax gets melted out. Let's wait for this icon to go away. The wax gets melted out, and then the molten metal is poured in or injected in, sometimes under pressure. Sometimes they do what's called centrifugal casting, where they put the casting on like an arm that swings around, and then they pour the molten metal in so that the centripetal force kind of squeezes the metal into there. It's actually really common how like jewelry is made and things like that. That's again, it's a lot more cost effective if you're just doing a few or one to set up something like this than to try and die cast. Say something like gold jewelry or whatever, because everybody's got different sizes. Sometimes people want custom items. So that's why investment casting, it's called investment because you lose all the wax, you lose all the plaster. So that's what we're looking at here is an investment casting. You can cast all sorts of metals this way: steel, bronze, titanium, all sorts of, this may even be a titanium part. All sorts of things, starting with lead, really low temperature, all the way up to very high temperature, because the ceramics can be made to withstand that. Alright, so molding. This is, again, very similar to casting, primarily focused on plastics, however. And again, some experts would group casting and molding into the same process, but we're taking plastic and we're not always melting it down. Sometimes we're just getting it hot enough that it's pliable and flexible. So that's why we're kind of talking about this, and there's a lot of different molding processes here. So again, it's a cross between casting and forming. So let's talk about injection molding. Super duper common process for high production rate items. It's very similar to die casting. So the molds actually look almost identical. So you take a hopper full of plastic pellets, you run it through this screw. So this screw actually does two things. It moves back and forth, and it churns up the plastic, and then it gets heated up. The plastic gets heated up through both the action of the screw turning and the shearing action and the friction between the pellets from stirring the pellets under high pressure. And then there's also additional heating bands around this. So most of the heat actually comes from the motion of the screw and the friction that is caused by that. And then the heating elements just kind of add a little bit more energy to that process. And then there's a valve in here it's not really highlighted in this image. There's a one-way valve in here, and then the ram pushes forward and injects the plastic under very high pressure, and it fills the mold. So it goes in through the runner and the sprue, and it hooks up here. We have the water cooling channels that we talked about even in the die casting. The mold splits apart. So in this case we have, it looks like a three-piece mold. We've got one half, two halves, and then a third half here, like a core half. My guess would be this is the piece that is fixed. So this piece right here, and then this piece and this piece go up and down, or this piece would be fixed, and then the two halves of the mold clamp together around it. And we've got these things called ejector pins, and I'm going to show you some pictures toward the end of the slideshow that actually show what these ejector pins do beyond ejecting the finished part. But they leave little what are called witness marks that really help you identify injection molded plastic parts. It's really easy to find and identify those that way. Moving on to blow molding. This is where we take something like a tube of plastic, a tube, a envelope, whatever you want to call it, some way that we can get air inside of the tube. So you take this bag of plastic, and you heat it until it's soft but not liquid, and then a mold clamps around it. So if we take a look here, we've got our plastic pellets. They get injection molded, and then this is almost like a continuous casting process being done here. We're taking our pellets, we're melting them down, we're forming them into a tube around this steel cylinder here. And we've got this solidified tube, and then the mold clamps around it, but the tube is still really hot. And then air is injected in, either from the bottom or from the top. Could actually go in directly through this tube. And then the high pressure air squeezes and stretches and pulls the plastic out to the very edges of the mold. And again, you get a very, very accurate product with this because it's cooling as the pressure is being applied, so there's no expansion or contraction issues or anything like that. You can replicate very detailed surfaces here because you're pressing right up against a nice hardened polished steel mold. So in this case, the example here is one of those big 5-gallon water jugs, and then the bottom is literally squeezing this piece off, so you've got to trim off a little bit here and a little bit off the top, but otherwise this is a mostly finished product ready to go out the door. So that's why those jugs can be so cost effective, because you're making lots and lots and lots of them, and the process is very quick and very simple. Very little hand finishing work to be done afterwards. Continuing the casting process, we've got rotational molding. This is how a lot of hollow plastic objects that can't be blow molded, they are rotational molded. These two processes are done with plastics. Usually, they can be done with molten plastics, but they're usually done with like two-part epoxy type plastics, where you're mixing two chemicals together that solidify in a certain amount of time. So like platinum curing plastics and things like that. So we mix a two-part epoxy, we put it inside of a mold. So you can take a mold like this. If you wanted this piece to be hollow, you take a mold like this and put very little resin inside of it so that it doesn't fill up the mold. And you put it in a frame like this where it rotates. So this is just a little hand-built rotational frame. So this is something that both of these processes can be done at home very easily. So as you rotate this frame, this string also causes the secondary frame, the inner frame, to rotate as well. So the molds that are in here are actually getting spun on two different axes, so it's like this big gyroscope kind of thing that's rotating around in all directions, so that by the time when the plastic starts to cure, it'll stick to the outside of the mold. It won't really stick on the inside. It won't form like a ball that rolls around. It just forms this outer shell and then leaves a hollow in the middle, so you can make lighter parts. So that's what rotational molding does. Kind of works really well for say you wanted to cast a jug or a container that was custom to you. That's kind of how you would do it, and then you just cut the top off when it was done. And silicone or RTV molding, this is where you take a material that's also a cast product. You make a mold maybe out of clay or something to make that's a positive image, and then you cast the silicone, which is what this part is, the bottom and the top, or it could be plaster in some cases. And you make a mold, a two-part mold or three-part or whatever, and then you take your two-part resin and you pour that in there, fill it up, and then close the mold shut. Or sometimes you just have an opening in the mold. It depends on what you're looking for here. And then you get a finished product after a certain amount of curing time. So this would be, both of these processes would be a low production rate because you can do 1, 2, maybe 3 at a time. They're custom made molds. And they're made out of silicone or rubber, so they don't last that long. They only last for a couple hundred castings at most. So Again, these are low production rate things. So if you ever have a custom made toy or something like that from someone on Etsy or something, that's most likely how it's made. These are really great processes to learn for just home making stuff, maker spaces and things like that. And ceramics are also molded. Ceramic molding is really interesting in that the product that comes out isn't cured. It's not done. It's what's called green. So um, slip molding and casting. This is where we take a liquid ceramic slurry. It's like I'm trying to think of what the consistency is. It's like thicker than milk, but still pretty thick stuff. Maybe like syrup, like breakfast syrup. Um, so you take that ceramic slurry and you pour it into a plaster mold, and there's special types of plaster for this. Um, it's a two-part plaster mold, and so you can see the two halves of this, and you can see the alignment pins here. Um, they align the two halves of the mold, and you pour it in there, and you let it sit for a prescribed amount of time. And depending upon your slip and your plaster, you can actually calculate what the thickness of the wall of the hollow part will be. So in this case, they're making a jug. Um, and then what you do is, after that certain time is up, you pour out the remaining liquid, which, because the plaster has sucked some of the moisture into it from the liquid, there's now a solid wall of material inside of the mold. And then you let that mold sit for roughly a day or so, and I'm sure factories can speed that process up. But you let it sit in there, and it becomes firm enough that you can handle it. Um, so you take that and you carefully extract the part. The part then turns into what's called greenware. So it's basically equivalent to clay, and then it can get fired, finished, fired, glazed, turned into an actual finished ceramic part. Press forming is a lot simpler. You take a clay. It's not a liquid. There's no special tricks to it. In this case, this is making it looks like a shallow bowl or a dinner plate. So this piece is spinning here. So you put the clay onto the mold, onto the there's like a form underneath here that's the inside of the plate or bowl. You press it down there, and then you push this arm. This arm creates this shape, and you can see it kind of cuts the clay a little bit as the clay spins. But mainly, it's just pressing the clay up against this underside mold here, and then the worker has a little trimming tool, so you can actually see this little bit being trimmed off here as it's spinning. Because it's such a motion-intensive process, it's actually really hard to find a good image. But basically, the clay just gets squeezed between two pieces. Sometimes it's just a stamping process, and there's no actual spinning involved. You just kind of squeeze clay between two mold halves, and then you trim the excess, and then ta-da, you have a final product. Removing the products from these tools can be tricky, though. Sometimes you just let them sit on this platter here. Sometimes air is injected underneath if you have ports for that. Sometimes you just very, very carefully remove them. But to not deform the clay is really tricky. Pardon me. Running this podcast style here. I had to get a drink of water. Okay, so then let's look at forming. So if we go back just a little bit, we're going to look at our secondary. So we talked about casting and molding. Now we're looking at forming. So there we go. So forming for metal, and we're going to talk about forming for plastic separately. This is where you take, and it's interesting. We take advantage of a process that in the metallurgical field is known as plastic deformation. Basically, that means you deform something and it does not return to its original shape. So, I might mention plastic deformation a little bit. That just means that we're squeezing something or bending something until it doesn't spring back to what it originally was. So this is forcing a solid into a shape with a metal die. So we're in this case, what we're doing, this looks like it's an ice climbing axe here, the head of one at least. So we're taking a metal blank or a metal billet, they're called, and we heat it till it's glowing red or whatever it might be, um, and and then we stamp it. And in some cases, it's progressive. So you see, if you look at this mold really closely, there's actually two slots in it. Um, the first slot underneath of the part here is most likely less detailed than the second slot. What that does is that's like a preform, and sometimes you can run into dies or molds that have 10 steps in them, where you take a chunk of steel or other type of metal, and it just progressively shapes the metal as it goes, and that's kind of what this stamping die is doing down here. So looks like it's a two-stage where you stamp the first part of the mold and it kind of gets close to the shape, and then the second stage of the mold here, which is this one, gives you pretty much the final shape. And you may even run this one into a third die, which can be done cold even, and that's called a trimming die. So that what that might do is like punch out a hole here or there, but it would actually, the critical part is it trims all this what's called flash off the outside, which is all the excess material. Because if you're short on material, it's not going to fill all these little nooks and crannies and the details in the mold. It's just going to leave a void, and sometimes they're hard to tell, and then you're really you're going to be out of luck. There's nothing you can do there. Um, so this is a forged part. Sorry, I forgot to mention that. This is a forged part. So it takes two dies, they're hammered together to shape metal into a product. Advantages to this: you get really, really tough tools that can last a long time. Um, Disadvantages: we're looking at extremely high production costs. Anything that requires a steel mold, I hope you're seeing a theme here, is extremely costly to produce these molds. They can cost anywhere from $20,000 to $500,000 to make, depending upon how complex these are. This is on the lower end because it's there's no moving parts to the mold. Um, you just attach the top half of it to one part of the machine, which is this guy up here, and then the other half to the anvil side of the machine. And then as long as everything's lined up, the top and bottom line up just fine, you're good to go. So it produces really, really tough, strong products, but again, very costly. Stamping, again, very high production rate sort of thing, because you're looking at, this is a much more complicated die. Less detail, less polishing that has to be done. You can kind of see like how shiny this material is. But down here, we're looking at a really complicated process. So we're producing this little kind of L-shaped bracket with a few holes and this little bent step in it. But this comes off of a long coil of material. Basically, back here you'd have a big spool of material that's feeding out this sheet metal, and the die is going up and down really, really rapidly. It's probably auto-fed, would be my guess. And it just goes doop, 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 doop. And every time the metal stamps, little ka-chunk, 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 a part gets spit out, but then new material gets fed in, and it looks like step one is punching this hole, step two is removing this little bit of material and this phase up here, step three is one of these two little holes in the slot. Eventually we get into bending and shaping, and then eventually the part is cut off. This is because if you were to do this in one little piece, it'd be very ineffective. So you'd lose a lot of material in the process. Here, this saves material, and two, it might just be too difficult for one die to make in one shot. It could dull the die very quickly, or the machine itself would have to be huge. You can get away with a smaller machine when you have what's called a progressive die like this. So a lot of sheet metal parts are stamped. I cannot emphasize enough. That is the primary process by which parts that are made out of sheet metal are shaped to their final shape. And by the way, going back up to forging, a lot of tools are done this way. That's high quality tools are made that way. So continuing with forming, so these should be more familiar processes to at least students in my metal shop. This is where we're taking solids into shape with a metal die. So here's a press brake. This is a kind of a close-up of how press brake works. This is our Diacro bender, not ours, but similar to our Diacro bender, where you take this target piece of steel, you clamp it into place, and then you use an arm, a bending guide to kind of wrap it around a die in one direction or another. So this is a huge catch-all. There's a million different ways to bend metal by hand or with presses and things like that. But yeah, bending very, very wide area, and they can be cheap. You can buy a metal bender that can be set up for basic production runs for less than $1,000. You could buy an automated, what's called a press brake, a machine like this, which has hydraulic rams that push this bending finger up and down, and the different dies and things like that, and they can cost hundreds of thousands of dollars if they're computer automated or huge. Because you can bend 1-inch thick steel and aluminum with a tool like this if it's large enough. Drawing. This is how wire is made in particular. Whether it's steel, copper, aluminum, whatever, you take a round bar, essentially, and you start pulling it through a thing called a die. Sorry, let me move my mouse away here. Start pulling it through a thing called a die. So that's this green piece right here, the mint green color. That thing is actually round. This is what's called a section view, so it's kind of a cutaway view. And you pull that round yellow workpiece bar through under extremely high pressure. Obviously, it's got to be less pressure than the material itself can withstand, so the material doesn't break. But you put it through at extremely high pressure so that it actually kind of causes this bottleneck in the material, and the material stretches out. So wire that's you buy for your house and things like that, that's all made using that process. Steel wires that hold up bridges, that's how those are made. The Roebling company actually got really good at that. The Roebling wire rope company used to make wire rope for steel bridges, and that was one of the processes they used to make their wires. So very interesting process, very high production rate needed because everything has to be calculated very, very, very precisely. Sometimes you need to do different heat treatment processes to make the wire be able to hold up to that process. Alright, so plastic forming. Very similar to how metal forging is done on an industrial scale too. So here we've got vacuum forming. This is where we take a solid sheet right here, so that's our blue sheet. And then we've got a mold, so that in this case we're making some kind of a bucket or a tray. We clamp the sheet down so that it can't pull in additional material. We're purposely thinning out the material to a certain extent. And then you pull a vacuum underneath. So that's what this is showing. We're pulling a vacuum, so we're pulling a bunch of the air out. So because this is a sealed area, the atmosphere then crushes down and pushes the heated, softened plastic down into there, and it takes the form of the mold. And these vacuum holes are exaggerated. They're usually very tiny. But it gives you a nice formed product. So the shells of RC cars are often done this way. A lot of cheap plastic masks are made this way. Old school Halloween masks when I was a kid, that's how those are made. So you can see this is just a picture. So they took what looks like a carbon fiber. It's not actually carbon fiber, but textured plastic that looks like carbon fiber. And they pulled it over this ape mask and then the Darth Vader here. So again, the clamp frame right here, and sometimes the whole frame moves down. So this is one where your mold sticks up really high, but in this case, this aluminum frame right here would actually be moved down onto the part, and then the vacuum would be pulled to pull the plastic down. All right, so wood forming. This is not a very common process, but I definitely wanted to touch on it real quick. Um, because we have, so it's done essentially to bend wood, and a lot of people will say, well, you can't bend wood, but you can, but it has to be done in a very specialized way. So that's called steam bending. So what we do is you heat a piece of wood. Usually it's a thin strip. It's rare that you can get away with like a huge thick board, especially if you want really complicated curves. What the steam does is it kind of relaxes and hydrates the fibers. It also gets the lignin, which is like the glue portion of the wood composite, and kind of gets it into a soft, more plastic type state. Talked about plastic deformation. And then you place it in a mold, and then you clamp it to cool and dry. And that cooling and drying process actually takes several days. You can't just leave it out for an hour. It's not like as soon as it cools to room temperature, that moisture is going to take a long time to get out. So in this case, you see that he's got a box to hold in the steam. He's got a steam source. So this one looks electric. Some people just use like a stove or something like that to boil water. He's putting the wooden strip in there. Again, he's wearing thick leather gloves. He should be wearing safety glasses. And then he shuts the door, and that'll sit there. A piece of wood that thick, it looks like it's 1 inch by 2 inches or so. That's going to take an hour to steam enough, probably, where he can bend it. And then you can see he's got this tool to bend the wood into the form, and then he's actually got a separate drying form. It's probably so that he can, produce several of these. He's probably got several drying forms, so you can bend it. And that's how you just apply nice even force, and then this would be the finished part right in here. But you can see what's involved, the amount of material to produce the steam box, the bending form, and the drying form just to get one bend. So it's very rare that it's something you would do for like a one-off project, unless you could think of a creative way to form it. And down here we have a production mold. This is half of an acoustic guitar. So this is the strip of wood that's being bent to shape here. It's got some metal backing along the frame, but you can also see these custom clamping pipes and tubes that are added to it. So it's like a tube that goes through the mold, so you can clamp on both sides. Some all thread. Not a highly detailed thing, but it's quite a bit of work to get something like that. So this person probably produces a lot of guitars, not just the one. All right, so we've talked about casting, molding, and forming. So these are our more abstract, but the higher production rate processes mostly, except for some of the plastic molding. So now we're going to look at removal. This is probably what we're most familiar with, removal and joining, because these are like the common quote-unquote shop practices where we're going to be, drilling holes and welding pieces together and things like that. So again, this image just kind of goes through some of the basic, taking these raw materials and straightening them out. This talks about pickling and things like that. This is like pre-treatment of materials. But yeah, we'll talk about removal, then joining. So removal, there's a lot to removal because it's so varied. So under the term machining, we even have metal, plastic, and specifically cold metal and plastic machining. So any of these processes that I'm about to talk about can be done with both plastic and metal, and to a certain extent wood. It just looks different with wood. So drilling, that's a machining operation. Anytime you're producing chips, it's going to be a machining operation. So we've got sharpened drill bit drills a round hole through a spinning operation. Sawing, again, we've got a toothed saw blade removing little chips to cut a part to length or something like that. Forms a thin straight cut called a kerf. So that's what the the gap between these two parts is called. So then we have a milling machine, or a mill. This is a spinning bit similar to a drill bit, but it's a lot more. It's a lot sharper on all sides, not just at the point. And B, it's usually meant to resist what are called lateral forces. So a drill bit tends to bend if you put side to side lateral forces on it. A milling machine is actually the bits that you use for that are generally made to withstand those forces. So here we're cutting out a little oddly shaped pocket. My guess is this is a computer controlled machine, but you can have hand operated machines as well. So this thing can cut pockets and slots and grooves and all sorts of different things. You could go around the edge of this and round off the edges of this material if you had the right style cutter. So it's all based on the shape of the cutter. So this looks like a standard end mill. So it's basically like a drill bit where the point is flattened. But again, it can cut on all sides. So it can cut on the side, it can cut on the bottom, cut on the other side. So I could just literally go back and forth and just cut this part in half with it if I really wanted to. It gets a little dangerous at the end there, so it's not really what you want to do, hence why there are saws. But you could drill holes with this. If you're very careful, it's not great for the bit. That's why they make drill bits. But you can, milling is one of the primary machining processes. If you were to tell me I could only have two machines in a metal shop, it would be a mill and a lathe. So hence why these are on the same slide as well. And again, I want to just reiterate this. Plastic is basically treated in the same way as metal when it comes to machining, in a cold process. And then we've got turning. So a lathe is a single tooth tool. Usually it's single tooth. You can have some lathe tools that have more than one tooth. However, usually it's a single tooth tool. And again, the tool is fixed in place. It's the material itself that spins. So if we look, this is our stock here. It's clamped in what's called a three-jaw chuck, 1, 2, 3. The chuck spins. The tool, the point of the tool is right there. The tool stays put in that it doesn't spin, and then it moves along the part or into the part or whatever, depending upon the type of operation you're doing. And then the spinning of the material is what creates the shearing action and creates the cutting. So again, it produces really big chips here. We've got chips over here on the mill, and we can do, you can create a rounded part. You can drill holes, so you could actually put a drill bit in there, and the drill bit again stays put, and the material spins. But it's a good way to put a hole right in the center of a rounded part. You can make round grooves. You can make cut threads if you want to have interlocking parts. You could bore out holes. There's all sorts of things you can do with a lathe. Again, these are probably the two most universal machines to a shop. All right, so some more removal from metal. We've got grinding and abrasives. This can be, so grinding, it's funny, grinding, there's two ways to look at grinding. I don't know why I have this duplicate image here. Oh well, we'll just look at this one. Grinding can be very accurate, highly precise, working in the 10 to 100 thousandths of an inch. So really, really, so that's, a 10,000th of an inch is 4 zeros, and 100 thousandth of an inch is 5 decimal places, or 5 slots after a decimal place. So you're looking at extremely precise operations. So that's how we grind things like tools and drill bits. All these little bits have to be extremely precisely ground, so you put them in specialized machines that have specialized abrasives, and they just take really light cuts. But then we also have really raw, rough abrasive processes where we're grinding. So we're looking at down here. You're looking at a chop saw. We do the offhand grinder to remove, if you wanted to grind out a weld. So those are very imprecise processes. Again, very rough, very, very raw, not accurate at all. And then here, kind of in the middle, we've got a belt grinder. So this can be very accurate if you take your time and you're careful. You can set up jigs that go on these so that they're even more accurate. But again, this process is a little bit it's done by hand. It's not going to be accurate. Big problems with grinding that we run into. High friction produces heat, so if you're sharpening a tool, the heat treatment of the tool matters. So these two things kind of go against each other. So it's really important to manage that. All right, so thermal processes for metal in particular. We've got cutting. So this is for steel only. The oxy-fuel torch here. You basically use a torch. You preheat steel to a critical temperature, and then you inject a jet of pure oxygen that rapidly oxidizes the steel. Basically, it creates this chemical reaction that's exothermic, so it actually adds heat to everything, and it forms a cut curve. So you can see the torch head here forming a nice cut, but it also cut out all these parts as well. So there is this oxide slag that comes out of it. This can be done by hand, or there are computer-controlled torches, which are still very common in industry. But becoming more and more common in industry are replacing torches, because you can use them on any metal, are plasma cutters and laser cutters. Lasers are even more accurate than a plasma cutter. Plasma cutter is a little bit more accurate than a torch. But they use electricity and a gas, so lasers usually use CO2 or argon. Plasma cutters can use any compressed gas, usually, or any oxygen-rich compressed gas. So compressed air is always the best because it's easily accessible and cheap. But it uses an electrical arc and gas to produce either plasma gas or a very intense laser that heats any metal to its boiling point approximately, and then vaporizes it basically, and blasts it out of the way with the gas. So again, you wouldn't see a handheld laser just because they're too dangerous. But this gentleman here is using a handheld plasma cutter to kind of cut the end of a pipe off. It looks like very standard industry practice, safe. We have one of these in our shop. But lasers are almost, or I would say they are 100% computer controlled. I've never seen a handheld laser. All right. So this is you could call it a thermal process, although it appears to be relatively cool. This is a really expensive process called wire EDM. Basically, you take an electrode and you electrify this wire, and it goes around on a loop, basically. Sometimes you reuse the wire, sometimes not. And then you electrify it, and what it does is this dielectric fluid, which is, it's like salt water essentially, creates this reaction with the electricity, and it removes very precise amounts of material. So you can get these really, really complicated but super crisp, sharp-edged parts. So you can see here just how sharp these edges are, and that's just done with a wire and some electricity. You can even pocket out the material with what's called a wire electrode, or not a wire, an electrically displacing electrode, where it's basically a big carbon stick that goes in and does the same process. This is just a view of the electricity at work here. Very rare that you actually see that in the machine. And they make 5-axis versions of this where the wire can be tilted and angled and all sorts of things, so you can get really crazy complicated parts. This is a really expensive process, and it takes a lot to set it up. Always computer controlled, never handheld. So not common in industry in the sense that tons of parts are manufactured this way. This is usually how you make dies and things like that for forming and molding and stuff like that. So it's, this is to make tools, not to make finished parts. Go back here. Alright, so now let's get into wood. Wood I'm just going to cover real quick because a lot of the processes are almost identical. Again, we're doing machining here. We're just making chips. So we've got sawing. There's tons of different types of saws, table saw, chop saw, all that, miter saw. Routing, so that's similar to milling. So we've got a spinning bit that can cut on its side. So it does a similar process. A lot of times it's handheld, but there are computer-controlled versions. Turning on the lathe, again, a handheld tool, but a fixed single point tool. and the material spins. So very similar to metalworking lathe, but the tool is handheld. This is kind of like almost like a chisel. Drilling. So again, standard type of drill bit. You could use twist drill for wood. This is a spade bit. And we got planing and chiseling. So you basically take you're moving down a surface. There's planes that it's a big heavy machine where you put a whole board in, and it reduces the thickness of the whole board by taking what's essentially chisel teeth and just taking little cuts. Here, this person's planing by hand, so it's like one blade in there that he's pushing along, and this whole shoe is just to kind of hold everything together. And then joining. So let's talk about joining. So the one thing that's pretty standard across all materials, there's very few that can't be glued or epoxied together, is this process. So you're taking a liquid that cures to solidify. Curing can be drying, curing can be cooling, curing can be a chemical reaction. But it basically bonds two pieces of material. Sometimes they're the same, sometimes they're different, by flowing into the pores of that material and becoming solid. It's like reaching out with your fingers and grabbing into like a pile of sticks or something like that. You can really get in there and grab. Imagine if that's what the liquid is doing to on a microscopic scale to the surface of a material. In the case of a lot of plastics, they need to be primed. So if we look at this PVC pipe here, the purple stuff is not actually the glue. The purple is what's called a primer. So it's kind of like it chemically activates the surface of the PVC to accept the glue. And it only works for so long. It's like a quick process. But this is how plumbing, with PVC at least, is glued. Wood glue right here. Really good stuff. It flows into the pores. You need a high clamping pressure in order to get really good results from your standard wood glue. And then this is just Gorilla Grand brand, but this is like a very universal type of glue where it kind of foams and expands, and it sort of flows into lots of other places. So you could do like wood to ceramic or plastic to ceramic, that sort of thing, with this universal type of glue. So they're just showing gluing a ceramic with it right there. More joining. So the other one that's universal to all materials is mechanical interlocking. So this is some people call it mechanical fastening. So you can use the material itself and the part itself, and you can create a joining member on it, or a portion of the part that then interlocks. So here we've got this is the corner of a bed. So we've got the foot of the bed interlocks with some of the beams of the bed, and it creates a solid connection. So there's no glue or anything necessary, no nails, no fasteners, just gravity sort of holds this one in place. And since you're putting something heavy on top of it anyway, it's very well held together. Just needs to be very precisely manufactured. Here we've got a plastic hinge. So there looks like a plastic pin through here, very flexible. And then the plastic itself, it's actually fused to another plastic sheet, but let's just look at the hinge pieces here. The mechanical connection is right here where these pieces loop together and they're sort of forced together, but it can bend and move. That's sort of one of the nice things about it. Here we've got a rivet. Very common, used to be even more common right around turn of the century, 1800s, 1900s, for building. But basically you take your two pieces of material, one end is pre-mushroomed of the rivet, and then you mushroom the other end over, so that there's no way they can come undone. So imagine if you did a grid of these, like 9 of them, in a 3x3 grid, you'd have a very strong connection because you're pulling and squeezing the material together, and there's no way that it can come out or come loose unless it breaks. And we've got mechanical folding seams, so that's done especially with aluminum and small sheet metal products. That's how like the lids of cans are held on. We've got double folded seams here, and we got our very standard bolted connection where we're taking our threads and nut, so external threads, internal threads to interlock, and tightening them down, and basically friction winds up holding everything together. Alright, just had to get a little sip of water. Um, Joining for metals and plastic, we can do welding and fusing with that. Plastic welding is not so common, so commonly done by hand. This was just the best image I could find that showed a good example of it. Where you basically take the equivalent of a soldering iron, you set it to a very precise temperature that for that type of plastic, and then you feed in a filler plastic. You kind of melt it into the piece. So this is where you're actually melting your two base pieces and then adding filler. Same process with metal. So you're melting the base materials of both the parts. You're having them flow together, and then most of the time, sometimes depends on what you're doing. Third filler material is added. So in this case, this is for welding steel. We've got the gun. We create an electrical arc that melts the whole area here. Got a shielding gas that's protecting this MIG weld. And we're adding filler wire, so you can see that turns into little droplets. It mixes with our base materials and then forms a weld. Same process. Plastic is done ultrasonically or just with heat. Heat generated by electricity, but the heat is what's doing that. Metal is done with heat generated by electricity as well, but on a much higher scale, as you could imagine. More joining of metals, brazing and soldering. So that's done. Essentially, it's gluing. This is an adhesive process, as I've said in class before. We're not melting our base metal. We're just flowing another liquid metal that melts at a lower temperature into the pores of our base material, and as it cools and solidifies, it's then locking into place. So technically, I could probably throw this in with our gluing, but it's worth having its own thing here. So here we've got a soldering iron. This is a literal soldering iron, and then this person is melting solder into this joint in copper. And then here this is brazed, so this is done with a torch, and you feed in a bronze or brass wire into here to then join these two pieces of steel. Okay, we're almost done. This is where things get beyond the scope of our class, but I just wanted to touch on these because I don't want to leave anything out. We've got additive manufacturing, and then we'll talk about conditioning of materials, which primarily focuses on steel and other metals. So additive manufacturing, that's what we think of that's what we're talking about when we think of 3D printing. So this is our basic 3D printer setup here. This is I bought a $300 3D printer. This is how it works. Takes a spool of plastic material, it heats it up, the nozzle extrudes it. Now normally there isn't such a huge gap here. Normally that nozzle is right down on the material. And then it builds up layer by layer. So it's going to build a layer, and then the platform moves down, and then it builds another layer, and that process keeps moving, and then the nozzle moves back and forth, and sometimes the table moves too. Here we have a secondary support material, because that's how we build overhangs. We fill up with a material that can be removed later, or sometimes the slicing software will actually create what are called break-off supports that are made out of our object material, and they're kind of temporary. So that process is called fused deposition modeling. We've also got stereolithography. That's what's shown here. You take a liquid resin, and then a laser or some kind of light at a very pinpoint accuracy is projected into that liquid resin, and basically it's a photopolymer, so it reacts to the very intense light and sometimes heat, and it solidifies in a really, really precise thin layer. And then this platform then moves down, and then the liquid's allowed to flow over the top of the solid object again, and then the laser kind of goes over and does the next layer. This process is being reversed right now. You can actually buy a liquid 3D printer where the light source is actually in the bottom. It's basically a really bright LCD screen, and then the platform goes up. So the platform starts on the bottom and then moves up and kind of pulls the object out as it's built from the bottom. Those are really good. That's really good for fine details. And then for metal 3D printing, a lot of people talk about it like it's amazing. really is a cool process. However, it does have its limits. So this is what's called selective laser sintering. So you take this ridiculously fine powder that has not been exposed to oxygen. If you were to expose this fine metal powder, any of them, to oxygen, their surface area is so great that the oxidation reaction that happens would basically cause it to explode. Um, so this is an oxygen-free environment, so not very practical for home use. And then a laser goes over layer by layer, builds this thing up. A layer of powder is raked out by the machine. It gets lasered in the area where it needs to be printed, so to speak, where a layer needs to go. And then the laser melts the powder so that it forms a solid. And then the next layer is raked out, and so on until the product is built from the top up. Problem is, it needs to be fixed to something, so this is stuck to a metal plate on the bottom, so that needs to be cut off afterwards, which can be very laborious. And again, it's kind of a dangerous process. If oxygen gets in there, it's dangerous. It's also dangerous for the worker to have to go into an environment where there is no oxygen. And then more common than you would think, is powdered metal sintering. So this is very fine metallic or ceramic powders. You could do either. With a binding agent are pressed using basically the equivalent of like a pill press. It's really concentrated press into a form, and then it gets fired. It gets cooked, so that it's kind of the shape, sort of all the powder binds together. So here's a little outline of the process. You take, whatever it might be, could be a ceramic too. Mix your powder. You squeeze it in a press into a very specific mold to essentially the final shape. And then you run it through an oven that gets it really, really, really hot. And then while it's still really hot, usually, you put it into a secondary press that does the final sizing of the part. To get it super hyper accurate. So you can get really complicated geometry with this. You can see some of these parts here are rather complicated. It's really common to make small gears and small clutches and things like that for power tools that are handheld. So like your cordless drills and things like that. A lot of their metal parts are powdered metal sintered. So very common industry practice. It's also, they can make really tough parts, very accurate parts. It's very waste free. Because imagine if you had to drill this, had to machine this, this sprocket here out of a solid bar. You'd have to cut all these teeth. You'd have to drill a hole down the middle. You'd have to cut the keyway. Here, you just use the powder you need, and then that's it. So very little waste, but the mold that I make for this can only make this one part, and so there's almost no flexibility to that. All right, last but not least, heat treating. So conditioning of materials. Conditioning is essentially, how do you get the part, now that it's shaped, to a state where it can function in the environment that it needs to function in. So this is really common for when tools have to be really tough, or for cutting tools or whatever. So if you need something to be soft, in the metal world at least, you've got annealing. So what you do is you heat the metal to its lower critical temperature. In other words, not melting, but hot. And there's certain temperatures depending upon the alloy. And then you cool it in a certain way. Sometimes you have to cool things very slow. Sometimes you have to cool things very quickly. Sometimes you have to cool things in a certain type of chemical. It depends on the metal. But the eventual goal is to produce a very soft part. I couldn't take a steel part and then squish it between my fingers, but if I had a copper sheet that I could use for a knife, and then I annealed it, I could crush it in my hand. I might cut myself, but it would be very soft. And then just the opposite of annealing is hardening. Again, same process. We're heating it up to a certain temperature, and then producing a hard, brittle part out of that. Primarily, this applies to steel. because steel is what we're making hardened tools out of. So for knives and axes and anything that's really got a cutting edge, that's the most commonly hardened part. But all those metal dies and things like that for stamping and forming, those also need to be hardened material. But it does produces a hard material that holds an edge really well, but it's also very brittle. So we want to take some of the brittleness out of it. So that's where tempering comes in. This is where you're heating to a much lower temperature, and you can see these are examples of steel here. So a lot of times with say I was going to temper a bladed tool, we would probably temper it somewhere around the 440, 500 degree range. The straw, people say look for a straw color, but probably somewhere around here. Especially like an axe, you want to go a little bit hotter. What that does is that removes some of the brittleness out of it, and then reintroduces a little bit of toughness. Toughness being the ability to absorb energy, and not crack or break. Because when a piece of steel has been properly freshly hardened, it's very brittle. If you drop it on the floor and a thinner portion of it hits the floor, it'll chip or shatter. So tempering allows it to absorb some of that type of energy. Alright, so we've talked about all these processes. We've gone over a lot of different stuff. I definitely strongly urge you to go back and review those processes as needed as we go deeper into this unit over the next few weeks. But now that we know all these processes, now we want to talk about how do we select the correct process. And the truth is, there isn't always a perfect solution for that. Sometimes it's very obvious, but sometimes it's not. Especially when you're doing things in small volumes, like we do in our shop or our lab. It's really important to identify some key factors that will help you select a process. So primary manufacturing is done at very large scale, can be continuous or batch processes. That's not really going to impact your process selection. That's kind of done for you most of the time. But I just want to talk about continuous and batch because it's going to lead into what we talk about with secondary. So continuous is sort of like that continuous casting machine where you're constantly feeding raw material into a machine and then producing parts or product out. Maybe you pause for a shift or something to adjust and clean the area or the machine, but generally speaking, it just kind of always does its thing. Batch processing, think about like baking. If you're working in a bakery, you have large ovens and things like that. You're going to make a batch of dough. You're going to shape the batch of dough, and then you're going to put it in the oven, and it's going to come out. So you're going to do like a few hundred rolls or something at a time. But you're not 24 hours a day feeding flour into one end of a machine, getting rolls out at a bakery. Large scale production might be a little different, but that's essentially an example of batch manufacturing. So secondary manufacturing can be done in continuous batch or custom. So it can be done at very large scale. So think about the production of like iPhones and things like that. You're talking tens of millions of products there. So that's very, very large scale manufacturing. Medium scale, meaning up to 1 million parts or so, usually less. Small parts. Small scale. This is what most local manufacturers in our area are doing. They're what are called job shops or job manufacturers, where they don't just make one or two parts. They're a very nimble manufacturing setup where they have a lot of different machines, but they can all be adjusted and changed easily in order to adapt to small batch production or custom production. Not a lot of continuous production once you get below very large scale production. And then custom production, again, we're talking one-off or 10 of something. You're not talking, 10 would even be a batch, but this is repeated batches. Custom would be, hey, I need you to make me these few things, and this is going to be it, or repairs and things like that. So that again, continuous batch or custom for secondary. So let's talk about how do we go through all those processes we just talked about. How do we choose one? It's difficult, but there's some guidelines we can follow. So some considerations for secondary manufacturing. Number one is the material being processed, because as we looked at before, that really dictates your starting list, which for some materials can be very long, for some is a little shorter. Um, but that at least gets you started. And then you want to look at how many of these things do I need to make, and I would actually interchange these two. They can be, you know, these are kind of on the same level. So how many of a certain product do we need to make, and then the precision and accuracy that's required for that product. These two, those are your bare minimum requirements. If you can't make a product that's precise and accurate enough, then you're not even going to be able to do your production run and say you're making 10 or 20 of something. Not even going to be able to do it, so you won't get the job, or you won't get paid for the parts that you make. So these kind of go hand in hand here. But then after that, then we've got to look at, okay, now we've got some options. We've whittled things down based on our material and then our accuracy that we need and the amount that we need to make. Now what are our cost constraints here? So what's cheap enough that we can get away with making these parts at a nice low cost but still make a little bit of profit? That's what matters. If you're an artisan, like say you're a famous artisan blacksmith or something like that, where just get someone just buying a part with your touch mark on it, you can sell it for almost whatever you'd like to sell it for. um, that the cost constraint doesn't so much factor into that. That's why it's so far down here. Whereas if I'm let's think, what's inexpensive. If I'm Hyundai and I'm making cars, the cost constraints for each little piece that I put into my vehicle, because the margins on manufacturing cars are not huge. This might get bumped up to like here, where I might bump down precision a little bit. So, cost constraints are huge, but we need to think about that. Again, anything that requires a form or a mold, that's permanent, especially when it comes to metalworking, or plastic injection molding, things like that. Those molds have huge costs, so those would only be for high production runs. That's why when people are prototyping plastic parts a lot that are eventually going to get injection molded and be cheap, they'll start off with those silicone molds I referred to before, and then with steel, it would just be in metal. It would just be kind of custom made, one off. Maybe a blacksmith would help, or you might machine a part and then say this needs to be formed and forged later on when you go to ramp up production. But cost constraints are huge there when you talk about forms and molds, because you're making custom tools. And then the geometry of the starting stock and the final parts. So we have different tools and different processes for sheet metal than we do for working, heavy steel. Same goes for plastic. If you're starting with pelletized plastic, obviously you've got to form it into a solid piece first. But with working with plastic, if someone gave me a giant 2 foot by 2 foot by 2 foot block of plastic, I'd probably have to do some machining processes on that. Whereas if someone gives me a sheet of plastic, then my options, I could do I could do blow molding if I formed it into more of a tube shape. If I could do vacuum forming. There's all sorts of different options. Again, that's just chemically it could be the same material, but the physical geometry of the starting stock does matter as well. And then last but not least, and this is the reason why I put this down toward the bottom, is because it's not often in consideration, but what are the personal values or the company values that they want to express? So like Starbucks talks about, fair trade coffee and things like that, and they like to emphasize how well they treat their workers. So their production values may be different than, Maxwell House or something like that in the manufacturing of their coffee. So that may affect the manufacturing process that they choose for certain elements of their manufacturing. So again, this is really an important list going forward. Probably want to be able to reference this often. So how do we then take all this information? We just went over process selection, and then we went over all those manufacturing processes. So how, what's the end goal here? Part of what I would like you to do is we're eventually going to look at reverse engineering parts. Not that you're going to remake parts, but I want you to be able to identify how parts have been manufactured. It's something that I think really helps when you're repairing a part or trying to make a replacement part or trying to identify, is this part worth the money that I'm going to buy it for? Is this thing, is it well made? Is it not well made? Is if I'm about to spend $300 on a cordless drill, you probably don't want to take it apart, but being able to see some identifying characteristics of a well-made product is really important. That's why we're talking about all this. It's kind of the end goal here is, if you can identify that the high-quality manufacturing process was used on a product, then it's really going to enable you to spend the proper amount of money on something. So let's look at this reverse engineering here. So some key questions to ask when identifying what processes were used in the manufacture of a product. So what did the product cost? Number one. Okay. Was it cheaper than you thought or not? You're eventually going to be finding things around your house and kind of identifying that. So you might have to ask someone who bought the product, what does this thing cost? So was it less costly than its cousin, so to speak? The average product in that family, or was it more costly? What materials have been used? This is tricky. But generally speaking, you should be able to tell, is it plastic, is it metal, is it wood, or something like that. If it's metal, one of the ways that you can check to see if it's steel is, does a magnet stick? If a magnet sticks, then it's steel to some extent. It's funny, one of the things about kitchen knives, really good example of this, you can see tooling marks all over them usually, and you can judge the quality of the steel with a magnet. Stainless steel, which is what a lot of common kitchen knives are made out of, does not hold an edge very well, but it's stainless and won't rust. Counter to that, a really high-end knife is going to rust because it's made of more on the end of regular steel, but it holds an edge really well. So it's kind of this, a lot of manufacturers try to find this balance between the stainless properties of stainless steel and the edge holding qualities of regular steel, like a tool steel. So sticking a magnet to your kitchen knives proves one of those or the other, not necessarily both, and I can't tell you whether or not that's a good thing or not. But that's a common thing to check for with a kitchen knife. So then, what tooling or manufacturing marks can be identified? I could teach a whole year-long course just on this, where we took things apart and identified how they were manufactured just by looking at the tooling marks. There are ways that manufacturers hide them. There are ways that manufacturers get rid of them entirely. However, there's a few things to look for. So a sheared edge on a piece of metal. What that's going to look like is about a third to half of the way through the thickness of the metal. So you got to look at the very edge of the metal. So if you're talking sheet metal, it's going to be really thin. But you're going to see a third or half of it looks flat and very smooth, like a knife has gone through it. And then another third of it looks crystallized and sheared off, like broken off. It looks like it's been snapped in half. It's got a really rough cut. So that's showing you that it's got a sheared edge. So most likely it's been stamped or run through some kind of a punch press sort of thing. So that would be a forming process where it's cutting, probably trimmed or something like that. Injection molding. Okay. This is probably the easiest thing to identify on plastic or cheaper metal parts, because you're going to have these things called witness marks. So these are the ejection pins right here. these little dots on plastic, and then sometimes you'll even find a date code that's in the mold. Um, this part in particular, this is like a gray plastic, but you can actually see it has thread. These are threaded inserts. So this is a piece of brass that's got threads in it, like the inside of a nut. So that the plastic, and they're probably molded into there, um, so that the plastic part can then be um, attached to something later. So, if you see something that looks like a piece of metal, but then you see these little brass inserts, that's another identification that it's plastic and that it was injection molded most likely. Um, so again, these witness marks and then parting lines and things like that on any cast part. So what that means is somewhere around the edge, you'll see like a seam that goes all the way around, and it's not necessarily always on one plane. Um, can't really see it on that. You can see a little bit of a parting line here. So the parting line on this most likely goes around the outside on one edge or the other. It's not usually down the middle, but a really good way to find a parting line on something is look at like a milk jug. You'll find kind of like an edge that goes vertically around the jug. So like from the spout down to the bottom. That's what a parting line looks like. Milling or turning tool marks. So these are different swirl patterns and things like that. Grinder marks are usually in one direction, whereas milling marks are circular like this, and they're a little rougher. But you can kind of identify those. This is just showing what chatter looks like. That's not so much of a concern. And then turning tool marks will look very similar to milling machine marks, only they'll be radial. They'll go around actually they go around the circumference of a part, not radial. Grinder marks, again, those are extremely fine marks going in one direction. They're sort of hard to find. They're usually what a manufacturer would use to cover up milling or turning tool marks. But again, grinding marks, that's worth a Google. That's probably an assignment you'll have later on. What are the identifications of a grinder being used on something? Welded seams in metal and plastic. Seeing seams where things are put together. Manufacturers a lot of times, especially in really fine parts, try to hide these things for good reason. They want their product to look nice. It's not like they're being sneaky or anything. But they'll cover things up with paint, etc. Spot welding in sheet metal. A lot of times, a couple coats of paint will get rid of that. The very obvious, at least, little divot left by a spot weld. So it's actually pretty easy for them to cover up. So they do that. It also protects the material. And then filleted solder joints. So if you've got two very obviously machined and cut parts that are joined together somehow, if you see the joint between them has a very rounded inside corner or outside corner or something like that, odds are that's some kind of solder or brazing or maybe even epoxy. But if it's metal, it's going to probably be one of those. All right, so wrap up. I know this has been very long, but what have we learned today? We've learned about the basics of primary manufacturing processes. Those make our standard stock that we can buy from a supplier, and then get into a manufacturing setting where we can then turn it into, use secondary manufacturing processes. We've touched on each of the major secondary manufacturing processes. Again, there's a lot more to that. I could teach multiple years of courses on that. There are people who have college majors just in that get their doctorate degrees in manufacturing processes. So, we've barely skimmed the surface, and I probably skipped a couple things, and that's okay. But these are some of the most common ones across all these basic materials. Some of them are material specific, as we've noted. That's really important to know. You can't. There's no wood welder. There is products called wood weld, but it's basically glue. And then metal and plastic have a lot of these processes in common. Because they can be melted down, because they can be formed when they're heated, because they can be machined when they're cold. Usually machine shops, places that do a lot of metalworking, also work with plastic just as readily because a lot of the same machines and tools can be used to do that. That's a really important concept to keep in mind when you look at how plastic parts are made, because it's not always injection molded and liquefied and things like that. Sometimes large chunks of plastic are machined down, although they are expensive parts. So again, when we were talking about, does a product have value and things like that? Talking about why would we want to do this? Why is this important? Well, that's kind of where that comes in. You know, just because a part is plastic doesn't mean that it's cheap or ineffective. Plastic, it may cost more to make a part out of plastic sometimes. So being able to identify these marks and identify those sorts of things can come in handy. And then we reviewed the process that goes into the selection of these manufacturing processes. Again, cost is a huge factor. Um, this slide is going to come in handy in the future. So it is really important to sort of kind of think through each product that you look at over the next few weeks and say, hey, you know, what makes sense for this? Is this something that a huge number of are being manufactured, so each part needs to be made as cheaply as possible? Or, hey, is this a low production run thing and some little places making these, and so they need to be really flexible? So a lot of the more universal processes that aren't specific to one specific shape and part, the more basic machining processes are those being used on this. So I hope everyone enjoyed this. If you have any questions, please feel free to email me, and have a good day.